Guess so.
Wait, right? So what is 7th grade math class?
In math?
All right, let's
No, wait,
It was PE.
I was the only girl who got detention because I was with the guy.
get your homework out. Get your homework out so I can take a look, please.
What's wrong with our class today, Clark?
That is, I don't know where all these people are.
Orchestra.
School activities. I'm not saying, but
The orchestra.
was there orchestra?
I didn't know.
Daffy is clowning, I think.
Oh,
And
thank you.
like Tim and Carrie. And
Sydney in the locker room.
is there, yeah, there's multiple things.
Wrestling, I don't know if they have
They all-
a wrestler.
they all
She
told
went out
me
and did it
about
in the gym.
All right.
Oh wait, there's no wrestling.
Oh, they do that.
No, yeah, so I did it in the locker room. She was fixing her hair.
And then they saw you in the locker room.
No, and then Cindy went out and did it to Michaela in front of Miss Anderson.
I put 3 stars on it.
Well,
I have a bag. What a bag. I think I've been using your pencils for like the past 2 weeks.
I got popcorn soon. Is that okay? Butter stayed. No, that was actually last night when I was doing my homework. Oh, that's the first.
I got most of it done. Some of it I just looked at it. And
Yeah, I was so vigorously needed to do my homework.
No?
For number 41, my answer was maybe. I was like, yeah, that last group I attempted that part.
I can actually have I got better.
Did you guys get 42?
Yeah.
See, I put 3 stars
This
here.
one here.
Because I had no clue how to do it. I just looked at it. I was like, I looked at it for like 10 minutes. 42 through 48, and I put 3 stars on it.
Utter.
I know, and that one makes
I
sense.
did 79. Like,
What's the rest of it?
Hey, ask me.
Well, it was all
I'm
based
really
off
proud
of
of
like one
79.
thing. It was confusing. I had no idea.
Yeah, I'll tell you the word.
Red Mom.
That sucks.
That one right there. Red Mom. Red
I tried that, but.
Brett Maher. I have my table for the.
Well, I did it. I did.
Mine looks
I
like
tried
that
to
too.
find.
They give me like
Yeah,
answers.
Friday
I'm like,
night.
this
No,
is
there's
kinda
not one that
useless.
night.
Like,
Oh, yeah.
the answers are in the back. If you have the answer right there, it's like, oh, I know what the answer is now.
Like homecoming. Formal.
Then it helps you. You're like, oh, I can figure out the answer. Yeah, you figure it to the answer, and you know what the answer is. Like how it is in the back.
Nobody voted?
Did you guys the book? And then you figure it out.
No, they said non-formal and formal. But formal is not non-formal.
No, there's no way. They wouldn't.
They did. That would ruin stuff.
So I say they pretty much read
How?
Do any of the
How?
co-seeking.
How, Brittany?
it.
We're not talking to you.
Ow.
No, I'm curious.
With
What?
the survey with
33,
the
35,
winter ball,
37.
that said formal and not formal. That was either prom or homecoming style. There wasn't like a not formal, like casual.
Oh, yeah, but it came out formal, but we knew what you guys meant, so we put semi-formal. Because we accidentally, instead of putting semi-formal, we put formal. We never meant
The
formal.
derivatives.
But it's semi-formal.
See, I wanted that.
Clark, you on?
No, but my freshman American time were asking, so I can tell.
Yeah, you can tell them now.
So what can I tell them?
That
what?
it's like you dress like homecoming.
Yeah, so it's not
It's
prom.
like
Yeah,
kind
it's
of
on the
formal,
12th.
but
Fall
it's
ball.
not jeans. It's
Like
like fall ball.
It's like
I told him that's what I thought it normally was.
yeah,
So-
we were gonna cheer for you at the girls' game.
You didn't listen, you didn't hear them when they said it.
Yeah.
Obviously, that didn't happen.
We were gonna start yelling.
Oh, that's probably that. That's probably better.
I was gonna yell Clark. Yeah, and I was like.
I don't do enough to get around each year.
Oh yes, you
All right,
do.
no.
You sit there and you do the book.
Yeah. I don't do the book, but,
Or the iPad.
no, I don't do
Master P gets an member at the same time.
I'm just throwing in my
You just sit there and you know
Expertise.
take up some space. on the bench.
Expertise.
I throw out a few things.
Well, no,
We mimic
And Boyd says no when I say it.
Yeah.
I hear
we
you.
mimic Boyd
I-
while we're.
I heard one of your speeches at practice one day about like you just expect to get better just because you show up to practice.
Oh, that was one.
I heard.
Inspirational.
I
You
heard
have to
that you
actually
were the
work hard
coolest
to get
coach.
I heard that you're the coolest guy on the face of the
Okay,
earth.
alright.
I heard that you were the best calc teacher. We decided to give a little
Yeah,
calc teacher.
Somebody, it must be the end of the, it must be the end of the term. Alright.
Really the end of the world.
F cardiac, thanks, Ryan, appreciate that.
Okay,
That teaches
back
you
to
move
calc.
414. Alright. I wanna do number 42 first, very quickly. Was that what
Yeah.
people talked about the table? Now, we're not gonna go all the way through it, but just, they tell you that h of x is equal to f of x times g of x, and they tell you j, I'm sorry here, people that are gone, I forgot what I was doing. Since there's so many of them. All right, so on number 42, it says h of x is f of x times g of x, and it says j of x, and this is similar to those of you that had questions on that 43 through 48. They say that this is f of x divided by g of x, and then they have a table of information. Now, this is not really gateway test stuff, but it is certainly stuff that shows up on multiple things, midterm, AP type things, those kind of situations. But it also helps you to understand the concept of these rules. But here's the thing we talked about yesterday, that I was disappointed a little bit in our answer, and talks about function notation. If you look at the very first empty space in the column, they're wanting h prime of negative 2. So I will repeat this from yesterday. Before we can find h prime of negative 2, we need h prime of x. H prime of x. So we have a place to plug the negative 2. So, according to the product rule, h prime of x is, let's put it over here, h prime of x is f prime of x times g of x plus f of x times g prime of x, right? Alternate, take turns, that's the product rule. So h prime of negative 2 is very simply f prime of negative 2 times g of negative 2 plus f of negative 2 times g prime of negative 2. You just take everything, copy it. And so, I mean, I'm not saying you have to write all that out, but, you know, just don't be lazy. Understand, if you really get what it's saying and you can kind of do some of that in your head, I'm fine with that. But otherwise, the notation causes confusion if you don't use it. If you're confused about it, then be careful with the notation right out. So now you just look at these in the table, right? What's f prime of negative 2? They're just in the table, negative 1. What's g of negative 2? Negative 3. What's f of negative 2? 1. And g prime of negative 2? 4. So we get 3 plus 4, which is 7. And so h prime of negative 2 is 7. Okay. And then you do the same thing with j. The difference there is it's the quotient rule. So you write out the quotient rule, and then you do that. And so then you repeat that for each of those blank spots in the table. Okay? So that's 42. So while we're at it, let's go into the 43 through 48. Now, I don't want to do the whole section, but let's do, what is it, h? Is that the first one that's the product? It's h of x is what? X squared f of x. So then, what do we need to do? Well, we look at the table. They give us the f graph. We look at the questions, and what do they ask? They're asking, just reading quickly, they want h prime. They want stationary point. Of course, that involves h prime. On 45, they want concave up. Well, that involves what? H double prime, right? So we clearly need h prime and h double prime to answer those questions. So I'm going to go ahead and do h prime of x. And that would be 2x. No.
Oh, shoot.
f of x, x squared times f prime of x. So derivative of the first, leave the second alone, leave the first alone, derivative of the second. And then down here, h double prime of x is going to involve two product rules. So let's write that. So the first product rule will have derivative of the first, derivative of 2x is 2, leave the f of x alone, plus the, see, and I'm treating those as two separate things, so the 2x f prime of x plus, and now I'm doing this one, so derivative of x squared is 2x, leave the f prime alone, plus the x squared left alone, derivative of f prime is f double prime. So that's the second derivative right there. Now, like we said yesterday, here's two terms that could get added together, but you don't have to. All right, so now we go into the question. So they want to know h prime of 2. Well, h prime of 2 would simply be putting a 2 into here. Put a 2 for x there, put a 2 for x there, put a 2 for x there, put a 2 for x there. Just put a 2 in for the x. So 2 times 2 is 4. What's f of 2? You read it off the f graph. And what is it? Negative 4. 2 squared is 4. What's f prime of 2? That'd be the slope of that graph at 2, which is 0. So negative 16 plus 0, negative 16. That's h prime of 2. And then h prime of 0, no, what? H prime of 4 is the next one. Okay, then they say show that h has a stationary point at x equals 0. Okay, back to this. What's a stationary point? When h prime is 0. Now, we couldn't solve this because, I mean, we could factor out an x maybe or whatever. Well, actually, that's what we could do. Show that there's a stationary point at 0. So you'd actually have two ways you could do this. One way would be to just plug a 0 in for x right now, right? So probably the simplest way would be to just say, hey, plug in a 0 for x right now. So you get 2 times 0 times f of 0. Of course, that's going to be 0. And then plus, and then 0 squared times f prime of 0, and that's going to be 0. So you got 0 plus 0, that's 0. So you put a 0 in for x, and you do get an output of 0. So it is a stationary point. The derivative is 0 when you plug a 0 in for x. Or the other thing you could have done is started to solve this. You could have said, well, I can factor out an x, and I'd have 2f of x plus x f prime of x equals 0. Well, when does that equal 0? Well, when that's 0 or when that's 0. Well, that's when x is 0, and then I have no idea when that would be 0, but whatever. So there is a stationary point at x equals 0. Okay, what was the next one? 45. Concave up at negative 0.5. So what they want is, it's negative 1/2. We need to know that. Is it concave up? Well, if it's going to be concave up, what should happen here? We should get out a positive. We should get out a positive right here. Okay? So let's check it out. So we got 2 times f of negative 1/2 plus 2 times negative 1/2 times f of negative, f prime of negative 1/2 plus another one of that same thing, right? That's the same thing. And then negative 1/2 squared times f double prime of negative 1/2. Right? So let's go through that. So what's f of negative 1/2? On your f graph appears to be 2. 2 times 2 is 4. 2 times negative 1/2 is negative 1. What's f prime of negative 1/2? Now we might not care what it is exactly. It's negative, right? You know that. The f graph is going down there, so f prime's got to be negative. So we've got a negative 1 times a negative is positive. So what we have is a 4 plus a positive plus this was the same thing, so that's another positive. So far we got a lot of positives, right? And then what's negative 1/2 squared? That's positive 1/4. And then what's f double prime at negative 1/2? How would you get that off the f graph? Think of the chart. F double prime. F double prime. If F is concave up, F double prime is positive. What's this F graph? Always, right? This F graph is always concave up, so F double prime is always. So I don't know what F double prime and -1/2 is, but I know it's got to be positive because F's concave up. So I got another positive. So what we have here is we got a 4 plus a positive plus a positive plus a positive. That's clearly positive. So H double prime of -1/2 is positive. So therefore it is concave. Okay? That's how you would go about that. And then, so 46%, 48, you can do yourself. Then that gets into M, and that you do the same thing. You'll do the same exact thing. Okay, so triple question mark, no, triple star, is that triple star? Right? You got it? All right. All right, 79. Okay, this would be now, let's take what we've learned with product rule and let's show how that would apply in chapter 2. Okay, max and mins. They tell you that f of x is e to the x, do I have this right? E to the x cosine x? So that's some function, and they want to know what's its and from 0 to pi. So they want to know, so they ask what's its max value, what's its min, no, they don't ask that. What do they ask? Yeah, but I said they asked what is its max value, what is its, where? What's the difference between what is it and where is it? If it says what is the max value of f, what do they want?
Oh, that's a number.
They want the output. Yeah, they want the output. That's when we do list of candidates, right? And we get that output, we circle it. That's what is the max value. When they say where is the max value, the input. They want to know the input. So we still do a list of candidates. This is still a global max-min problem, right? Do you understand that? That's not local max-min. They say where is the max value? Where is the min value? It's still a global max-min. So it's still a list of candidates problem. And where are candidates? In points, and we plug them back into the original. So we're going to do f of 0. We're going to do f of pi. And we're going to find those values. Those are possibilities. What are the other candidates? Stationary points, where the derivative is 0. So we're going to need to do the derivative set equals 0 and solve that. And put that in our list of candidates. Okay, so we can find these two real quick. So e to the 0 is 1. Cosine of 0? 1. So 1 times 1 is 1. E to the pi, I don't know what that is, but now we're going to assume this is no calculator until it gets too tricky that we will cheat. But e to the pi would be about 2 to the third, right? Pi is about 3, e is about 2. They're both a little bigger than that. 2 to the third is 8. So this is going to be a little bigger than 8. And then cosine of pi is -1. So it would be somewhere in the -8 range. It's probably -10, 11, something like that. But it's -8 or -9, something like that. So at least it gives us a reasonable about where it is. Okay, and so now we need stationary points. So we do the derivative. And of course, we look at that and we say, oh, well, to do that, we got to do the product rule. See, and what I hope after yesterday you would never do, but sometimes we fall into this trap, that some of you just do the derivative of that, derivative of that. You can't do that, right? That's what the product rule says. You got two functions of x being multiplied, you've got to do the product rule. Okay, so derivative of the first, e to the x. Leave cosine alone. Plus the derivative, or e to the x left alone. Now, times a negative sign, and I think it would be best to stick the negative around in front. It's probably just best to do that. Okay? How you write this, especially with negatives, is really important for the gateway test. For those of you that want to pass the gateway test on the first try, is there anybody that doesn't want to pass it?
I know.
Okay. All right.
I'm going to
So-
take it again.
Okay, so for those of you that want to pass it on the first try, everybody but Riley, okay? You have to be really careful about those negative signs and how we write them. It's one of the big things, besides knowing the rules, obviously. I mean, somebody in the other class said, well, what if, or maybe you just don't know the rules. I said, well, if you don't know the rules, then you're not going to get 8 out of 10. It doesn't matter. I mean, that's a given. You've got to know the rules. But where you're gonna get in trouble is the negative signs and the algebra and the simplifying, and those are the things we're gonna be going through, some today and every day as we go along. You can, yes. If you write e to the x and then parenthesis negative sine x, that's perfect. That's great. I just think as you go on to the next step and stuff, what you end up then is putting it out front probably. I'm not saying you have to. If that's all the simplifying you can do, you know, having it there is good. Yeah.
So will we be doing extra practice for the hard problems for this?
Yeah. Matter of fact, I'm sure. Yeah, but
Is there any of this stuff like the derivatives that we did last chapter? Is it just strictly all these new like ways?
no, yeah, all the ones we did last chapter, like the rule for e to the x or sine x. I mean,
Just like
all
kind of those simple.
the log. Yeah, those. The last chapter, those would be the very basic rules of if the function is this, you do this. What we're doing in this chapter is we're saying, now what if we multiply two of those functions? Or what if we divide two of those functions?
It
Right.
could maybe like not all of them are going to be multiplied.
Right, absolutely. Well, the one we're going to learn today is what happens if a function is inside of another function. We've already talked about if you have 3x inside of sine x. But what happens if you have other functions inside? That's what we're talking about. That's the most important one because that's the one that happens most of the time. So they won't all be product or quotient. There could be some that the easy ones would be the ones like chapter 2. Right? You know, we talked about easy, medium, and hard. Turn to page 195 real quick. Just flip back to page 195. Okay, see that page full of problems, and then they continue over to the next page. Okay, now after today, we have a few new things to do. We've got to do the inverse trig functions, which we'll probably do on Friday. Tomorrow we're going to do this thing called implicit differentiation, but those are kind of smaller things. I mean, they're not. I mean, they're important, and you got to memorize them. And the one tomorrow is a little tricky, but really after today, you should be able to do almost all of them on page 195. And on your assignment sheet, the very last assignment says 3.5. That's section 3.5, which is just practice on everything. And so that's not really an assignment, that last one that says 3.5. Really, that is starting today. You should probably begin to do your homework, whatever the homework for the day is, and go to page 195 and pick out some and just do them. Pick out the odds maybe first. You can look them up in the back, or of course you have your calculator to check, and we're going to do that here in a little bit too. Okay? So you say practice on the harder ones. That has got a nice mixture of easy, medium, hard. Probably more medium and hard. Hopefully you don't need to practice the easy ones. I mean, if you do the medium and hard ones, then the easy ones should be okay. Now, right now, even the medium ones are going to seem hard, but after a lot of practice, and like I told the other class, it depends how bad you want to pass the first time. If you want to really pass the first time, then you'll do most of those problems sometime between now and Monday or Tuesday on page 195. Okay, so now is not a time to be conserving paper in your notebook as you get ready for this. But some of you are going to say, hey, I got this. I like algebra. I like this stuff. And you may not need to practice as much. Totally up to you. All right. Anyway, back to this. We now have to solve this. So what do? What can we do algebraically to solve this? Factor out, yes, factor out the e to the x. And you end up with this. So now either this or this have to be 0. So where does e to the x equal 0? Never. Because e to, well, yeah, very good. No idea why you're not going to be here next week. Okay, anyway, e to the x equals 0, never. The e to the x graph never crosses the x-axis, and e's a number raised to something will never be 0. E to the 0 is 1, right? It's just never going to be 0, so we can throw that out. So the only one we have is where does cosine x minus sine x equal 0? And that would be when, probably the easiest way to do this is add sine over to the other side, When is cosine equal to sine? Remember, we're looking from 0 to pi. No? Remember, cosine is the x and sine is the y in either circle. The only time that there are is root 2 over 2, which is pi fourths. Now, that's when they're both positive root 2 over 2, and then down here, they both be negative root 2 over 2. And that's negative 5, or that's 5 pi fourths, but that's not between 0 and pi. So the only one is at pi fourths. So that's our stationary point, so we add that to our list of candidates. So we've got e to the pi fourths. Now here's where we realize that maybe we need to calculate. E to the pi fourths, and then cosine, what's cosine of pi fourths? Root 2 over 2. Somebody type that into their calculator for me. E to the pi fourths times root 2 over 2. Now, with this said, now I make a comment about the quiz that you guys took on Monday. There were some of you that did not show enough work on the calculator problems. Did not. I could tell you did stuff on your calculator, and then you just kind of wrote down the answer. You lost a bunch of points. We talked about that. We talked about it many times. When you do a calculator problem, if this was a calculator problem as opposed to a no calculator problem, the only thing that would be different is I wouldn't have maybe this line and this line and this line. I would have this equals 0. So some of you didn't even have your derivative on the paper. Equals 0. Any of that. You just had the stationary points listed and where the local maximums were. You can't do that. You've got to have your derivative set equal to 0. You can use a calculator to solve it. You've got to have your list of candidates or your number line. You've got to have your rationale written out. Problem that's calculator or no calculator look almost identical as far as the amount of work that you have. Okay? All right. Anyway, what are you getting here? About 1 something? Seems to me the other class we had 1.551. Oh. All right. E to the pi fourths times root 2 over 2. Well, we'll go with that class. They're smarter than me. All right. So.
Well, I didn't actually do my own calculator, so I got last night.
Oh, very good. All right. Now, so let's answer the question. Where is the max value? The global max value is at x equals pi fourths. Where is the min value? X equals pi. That's how you would answer those questions. And your list of candidates would be your justification. Okay? And then inflection points. Oh. F double prime. Okay? Well, let me give you the short version of it because we got a lot of things to get to and I want you to have some work done. When you do F double prime, a bunch of things, you get a product rule here and a product rule here. And when you get it, a whole bunch of stuff cancels out or combines, and you end up with negative 2 e to the x, I think, sine x equals 0. Something like that. Well, e to the x never equals 0. We just said that. So it's just when sine x equals 0, which is at what? When does sine equal 0? 0, pi, 2 pi, but we're only looking 0 to pi. So 0 and pi. So we would do an F double prime number line. Now, somebody in the other class mentioned that I had said earlier when you have inflection points or local max min, we don't use the endpoints. Remember that? We said we don't look at the endpoints. Those are the endpoints. So would it be okay to say no inflection points? And I would say it would be. I wouldn't ask you one where it came out like this. Okay? On the AP test, I don't think it would either. But if you do it, I think you end up with something that looks like this, or it might be the other way around. I think it's the other way around. I think it's positive, negative, positive. So they are inflection points. I mean, you do get a F double prime does change sign here, so you do get a change in kaka. So they are inflection points, but they are at the end point. So sometimes we ignore those for inflection. Okay, so that takes into account that stuff. All right, so those are the problems I think that are ones that there's parts of this that are like the gateway where you have to do the derivative. But now let's get into like 19, 21 into that section. These are the ones that definitely are what the gateway is about. So where do you want to start? 19. So we got f of x equals 1 minus x cubed over 1 minus x. You were supposed to do this one two ways. First way was by the quotient rule. Right? So let's do that one first, because that's how you would do it on the gateway. This acts, and then you were supposed to do it with some algebra. Did anybody know what algebra to do here? Anybody without getting help from me? Do you remember how to factor that? Mrs. Andreessen would really be happy if you did. I talked with her yesterday. She said, yes, they should remember how to do it. A difference of cubes, which is what you have there, factors into a minus b times a squared plus ab plus b squared. Which means, that, so I'm working it backwards here, I'm doing the second part. Which means this top would factor into 1 minus x times 1 plus 1x plus x squared all over 1 minus x. One minus x is canceled. Now remember, this is still f here. Is this f or what? It's listed as h. Yeah, I'll call it. But anyway, so this is f. We cancel the 1 minus x, and so f is 1 plus x squared. Now what's f prime? Right? Derivative of 1 would be 0. Derivative of x would be 1. Derivative of x squared would be 2x. There would be your answer. So if you remember, you do not have to remember that algebra, but if you remember that factoring, it would certainly be helpful to you on the gateway. If I gave you one like that, that would make it a lot quicker than what we're about to do. Okay? But you may not. Okay, you may not. Probably not. Now we reviewed it there, so if you want to study it. Now I'm not saying that's going to happen that often. It's nice to know, but not probably have to. So now let's just do our quotient rule. We should get the same thing. So the quotient rule says what? Derivative top, so we got u over v, so u prime, so derivative top is, well, right, but okay. I'm not going to write it.
Oh,
Yeah, just tell me on this problem. So negative 3x squared, so derivative of top, derivative of 1 is 0, derivative of negative x cubed would be negative 3x squared, times 1 minus x. Ah. Look up here, look what I wrote. Parentheses. I mean, when I wrote that, if you were looking, a lot of you weren't looking. When I wrote that right there, I mean, like, you should get goosebumps. I mean, your skin should crawl when you see that. You should just go, yes, exactly. Put parentheses around there. It's driving me crazy. Fingernails on a chalkboard. You guys even know what that fingernails on a chalkboard? Do I even talk about it? Okay. Yeah, what's a chalkboard? Yeah, exactly. What's a chalkboard? Yes, and again, why are many of you not going to get, why are some of you not going to get 8 out of 10 on the gateway test? Not going to be because you don't know the derivative rules. It's because of stuff like that. You're not going to put parentheses around there, and then when you simplify it, it's going to be wrong. It's the algebra thing. Okay? So negative 3x squared, derivative top, bottom left alone, minus, tell me, in parentheses, the top left alone, derivative of the bottom is negative 1. Okay, probably put it in parentheses would be good. Always minus. Quotient rule is u prime v minus uv prime all over v squared. Yes, always minus. And then the bottom is 1 minus x squared. It's the bottom squared. Yeah. So I'm working under the assumption that we got that product rule, quotient rule, memorize that, the minus, all that stuff. Okay. All right. Now what? You need to simplify that. Now again, I talk about obvious simplifying. Obvious simplifying would be distributing and combining like terms, maybe factoring and canceling if you can. Okay, this one's not very obvious, this algebra over here. Okay, so I'm not worried about you doing that, but if you knew it, it'd be helpful, but you know, could be helpful. But on this one, so we need to distribute this right here. Okay, so what do we got? Negative 3x squared. Negative times negative plus 3x cubed. Now here's where we get in trouble here too. The minus on the quotient rule causes a lot of grief because this minus on the quotient rule, the one Riley just asked about, that minus is usually minus some stuff. That stuff needs to be in parentheses. That you're often having to distribute that negative. Now in this case, since it's times a negative 1, actually we can bring that negative 1 in front and this turns to plus. So it really ends up being just plus 1 minus x cubed. I mean, I could distribute that negative and then distribute that negative, and then they cancel each other out in the end anyway. So that time it's not too bad. All right, and then we get 1 minus x squared. Now what? Combine like terms on the top. So 2x cubed minus 3x squared plus 1. Now, some people want to get in a big hurry to FOIL this out. I usually am not, just because I'm hoping maybe when I combine these terms here that something can factor, maybe I can cancel some things. So I usually am not in a big hurry to FOIL that out on the bottom. On the top, I want to distribute those things so I can combine some terms, hopefully some things dropped out, that kind of stuff. Now, is there anything I can do up here? Factoring what? No, because there's just plus 1, there's not a common factor, it's not a quadratic, so I can't do a FOIL thing. So you look like you're pretty much stuck. Now you could go 2x cubed minus 3x squared plus 1, and then down here go 1 minus 2x plus x squared, right, like that. Like I said, that doesn't really do anything for you, but you could do it. On the gateway, one of these would be fine. But wait a minute, I thought it was supposed to equal x. So that's a problem, right? What we can do is divide it. This is, I talked a lot to Mrs. Andreessen yesterday. This is something she said you should be able to do. But again, she's prejudiced because she taught a lot of you this. So she wants you to be able to do it. Those are fun. But this one time, I'm going to show you this to remind you. In Algebra 2, and not just in Mrs. Andreessen's, I don't think. I think in the regular Algebra 2 class they did this as well. We do long division. Does that look familiar? Vaguely? Vaguely familiar? Because that's what this is. This divided by this. So what do you do when you're doing long division? You think, well, this times what would make this? Well, it'd be 2x squared. No. 2x. 2x times x squared is 2x cubed. 2x times negative 2x is negative 4x squared. 2x times 1 is 2x. Oh, those don't line up. I need to move that 1 over. I need to put in a 0x there so everything lines up. And then my plus 1. Now I subtract. 2x, subtract that, that'd be negative, that'd be 0. Subtract the negative, that's positive, so that'd be 1x squared. Subtract the 2, that'd be negative 2x. Plus 1, look at that. 1 times x squared is x squared. 1 times negative 2x is negative 2x. 1 times 1 is 1. Subtract those, 0. So that divided by that does equal that. It turns out that the top did factor. The top factored into 2x plus 1 and x squared minus 2x plus 1. So the top did factor, and then on the bottom we had x squared minus 2x plus 1, and then those canceled. But who would have known that it did factor that way unless you divided it out? Okay? So on the gateway, these are the same. Now let me get your calculators out. We're going to do a couple things on the calculator here. Let's say you're working at home. Okay? And you're working this problem right here. Okay? Say you're on page 195 and you're working some of those. Now the odd ones are in the back, but you're working an even one. Okay? So, you worked out this problem, and you've got, let's say to this one, you've gotten to the blue one as your answer. Okay? All right, you've gotten down to there, and that's your answer. You want to check if you're right. So you go to your calculator, and you do the derivative of this. Go ahead and type that in. The derivative of that, the original problem. Because this is, see, I think of your calculator as electronic solutions manual here for these derivative problems. Because all you have to do is go in, do the derivative, and it'll spit out the answer. Does it give you 2x plus 1? Okay. So you've worked it, you got down to the blue thing, and you do it on your calculator, it's 2x plus 1. You're like, crap. What did I do wrong? Well, before you think you did something wrong, take your answer and type it in. Because usually, not always, and I think somebody mentioned this, I think I talked about this earlier in a different context. Usually, if you type this in, it'll simplify it using kind of the same type of rule, and then you can see if they're the same. I think somebody else said all you have to do is take your answer, 2x plus 1 equals, and then type that in, and it'll say true or false. If they're equal. If they're equal, it'll say true, and if they're not, it'll say false. But if you just type in that blue thing and hit enter, I think it says 2x plus 1. And so then you'd be like, okay, well, my answer is the same as 2x plus 1. Okay, that doesn't happen that often where we get, you know. But like I said, the blue one would be okay on the gateway. But I'm concerned that you're working at home, you get an answer, and you're not sure if it's true, right or not. And I want you to be able to use your calculator to test it and see. And sometimes the calculator answer looks different than what you got, and then you're thinking maybe you didn't do it when in reality you did. Yeah. That would be silly. You know what I mean? Because it would just give you all the
Yeah, if somebody got
yeah, don't make them super hard. I'll just make them harder. So it'd take you longer to type it? No. No. Clearly, you will not be
We
able
get a time test.
to time to see how fast you can do the calculator. All right. 21 through that section. What do you want to see there? I know there's some questions about tangent and stuff, probably, right? What's 23? F of x equals the square root of what?
Just x times.
So my square root's way. Square root of x what? All right. So clearly I want to make that x to the 1/2. Okay. So product rule says what? You guys tell me. Not half x, just negative half. Times ln x. X to the 1/2. Right, this is a really good one because this points out some of this simplifying that we need to do, what I would call obvious simplifying. On this one, there's nothing I can do to it. I can rearrange it. Now, if you look in the back of your book, what they will do is they will take this negative power, flip it to the bottom with that 2. And they'll write 1 over 2 square root x times ln x. As a matter of fact, I think what they'll write is ln x on top and 2 square root x on the bottom. That's what I think they'll do with that one. I don't care about any of that. You can do it. I mean, if you do it, make sure you do it right, because you might miss it if you do it wrong. But otherwise, just leave it like that. There's just nothing else to do with that. Now, there will come a time where we'll need to do that. If this is a stationary point problem and I need to solve this equal to 0 without a calculator, then I probably need to write it like that. That's probably going to be helpful. But for right now, we don't need to. So we just do the derivative and we get that. All right, this one we definitely need to do something with. This is x to the 1/2 over x to the first. We can subtract those powers, or I can bring this x up top as a -1, however you want it. But what's it end up being? It ends up being x to the -1/2. So this final answer could look like this: 1/2 x to the -1/2 ln x plus x to the -1/2. That would be a fine stopping point.
Yeah, I doubt that.
Okay? So, what did they do in the back? Look, there's all kinds of things in the algebra. And if you type this into your calculator, your answer on the calculator will not look like this. It'll put it into square roots and everything else. So that's where what I would do is type yours in, get equals, type theirs, or what the calculator gave you, and see if it says true. If it says true, then you know yours is the same as that, and that's fine. Because, and this is good, this is a perfect one to look at. Because what I said I want to do is talk about what do I expect you to simplify and so forth. Couldn't we factor out an x to the negative 1/2 here? Both of these have an x to the negative 1/2, right? So I could factor that out. That's where that +1 would come. If I factor out an x to the negative 1/2. But why do it? I only think you need to factor if you can cancel something. If I've got 3x plus 6 over 3, then yes, I want to factor out that 3. Because I get x plus 2 over 3, and then I can cancel the 3's. So I definitely want to factor out that 3. But if your answer is just 3x plus 6, do you need to factor out that 3? I mean, I can factor out the 3, and then it just sits up there and nothing happens to it, so I don't think you need to do it. So if the answer is 3x plus 6, just leave it 3x plus 6. But if it's that other one, I factor out a 3 and can cancel it, then I should factor out the 3. So factor it out if you can do something with it, but here, factor out an x and a 1/2 doesn't really help. Now, if I find stationary points, setting it equal to 0 solving, yes, that's what we would do. But for this, I would stop right there. Okay? All right, good. Next. What's 31? Is that the...
That is f of x equals x plus 1.
Okay, this will be a good one. And then let's do the tangent. Let's talk about tangent. And then we'll get into the new thing today, which is fairly short. And then we'll get to work. All right. So, first of all, is there anything we can simplify? And it feels like there should be, oops, but on the bottom, there's just nothing you can do with it. As much as you want to, you cannot factor x squared plus 1. There's just nothing you can do. So you're not going to be able to simplify it. You could FOIL out this top. In some ways, that might make it easy. Okay? But did anybody do that? Or did you just go with it the way it was? The way it was? Okay, most people probably do that. If you FOIL it out, fine. Okay, it should end up the same. All right? So, here we go. Quotient rule. Because we have a quotient. So the derivative of the top would be what? 2 x plus 1 to the first. And we don't have to kick anything out, right? Times x squared plus 1. Oh, good. Parentheses.
I'm just good enough to remember it.
Minus
X plus 1 squared.
top alone. 2x. Now, you actually wouldn't needed the parentheses there, but man, you know, it doesn't hurt. Yeah, well, and to be honest, I don't want to over dramatize that because I have seen people just, they start throwing parentheses. You keep talking about parentheses, okay, I'll put, and you start putting parentheses all over the place, and then that can mess you up. So, I mean, you know, you've got to do where it needs to be. All right, but usually the mistake is to not put them in where and you need them. All right, so then you end up at the bottom square. So again, it's very much like the last one we did. There's a little more work to do here from a algebra perspective because we need to FOIL as opposed to just distribute. So let me do this. I would FOIL this, and then we'll distribute the 2 through. So first times first is x cubed. Outers would be, let's do the inners because it's squared. Inners would be x squared. Outers would be 1x. Last times last would be 1. And then every one of those are going to need a 2 on it, right? Because we now have to distribute the 2. So 2, 2, 2, and that 1 returns to 2. So I FOIL it and then distribute a 2 in. Minus, and then this is the one we got to be careful of, so a big set of parentheses, we're going to have to distribute that minus. Actually, to be honest, you know what I think would be easier here, because and it'd be a good time to talk about it, because this is something that happens a lot. I think it would be best to think of this 2x around front here and think of this negative as attached to that 2x. Now when I distribute, I'm not going to distribute a 2x, I'm going to distribute a negative 2x. And you're going to see in a later problem where that's a good way to think about it. So this one, FOIL out first, is going to be x squared plus 2x plus 1. Then I've got a negative 2x out in front that I'm going to distribute. Right? That's that right there. So what's that going to be? That's going to be a negative 2x cubed minus 4x squared minus 2x. So that's all the top stuff. So now what happens? Well, it looks like a bunch of stuff cancels, which is nice. The 2x cubes cancel. The negative 2x and 2x cancel. So it looks like I end up with 2x squared, negative 4x squared. That would be negative 2x squared plus 2 all over x squared plus 1 squared. Does that look right? Now, this one, I mean, there are guys that ask me, is this hard one, medium one? I don't know. Hard one from the standpoint of there's a lot of places you can make a mistake. And on the gateway test, it's all or nothing, right? It's either right or it's wrong. And so there's a lot of places you could mess up something. And the algebra is not that tough, but there are a lot of different places you could screw up. So this might be borderline on the hard side. What now? Are we done? I mean, what could we try on top? We can factor out a 2. How about negative 2? Because what I'm thinking is, I'm looking at this x squared plus 1. I'm thinking about factoring or canceling. If I take out negative 2, I'd have x squared. That was close, but it didn't quite work. I was hoping for an x squared plus 1 then, but it's an x squared minus 1, which would factor in x plus 1, x minus 1, but it's, again, still nothing cancels. So it would have been okay to leave this. We tried this in the other class. We typed this in. We typed the derivative of this, and it came up on the calculator, negative 2, x plus 1, x minus 1. And then on the bottom, it just had x squared plus 1 squared. That's what the calculator said, which is the same thing. So either of these would be okay. Yeah. Yes. The what? This squared, you mean? What that would have, yeah. No, it's a good question. If this would have been this, is your question, right? Yeah. Okay. What this means is you have one of these up here, and you have 2 of them down here. So if one of those canceled, it would basically do that. Yes. Okay? All right. Well, but seriously, I mean, those are the ones that when I hand back on the gateway test and you got 6 out of 10 and you look at like 3 of them and go, duh. You know what I mean? That's what you do. You're like, oh, geez, I knew that. So, I mean, so even the things that seem obvious, let's make sure we do those. If we take care of those, we'll be better off. All right, let's talk about the tangent one. Now, I think 39. Did 39 have tangent in it? 37? Well,
No, I think you're talking about 35.
no, I'm talking about. 37 said g of x equals secant squared x, and big G of x equaled tangent x. All right. Now, the question is, did you flip back 2 pages and look in the book? And if you did, I didn't tell you about tangent, cotangent, secant, did I? I didn't.
No.
I didn't tell you about those. Purposely, number one, if you want to look at, if you look at the back of the book, that'd be great. But I also want you to think about the product and quotient rule. Now, from this point forward, now tomorrow, one of the things we'll do tomorrow is write down a list of where are we with rules. What are our rules that we should know right now? And we'll make a big list of those, okay? And those 4 that, well, all 6 of them, I think, are over there, of the trig derivatives you need to know. You just need to memorize. So But first of all, I want you to understand that how would you test that this is the antiderivative? Do the derivative of it, right? You would do the derivative of big G should equal this. And that's what that table said, okay? So you just look at the table, you'd say, yes, it is, okay? Well, let's do the derivative of tangent. Well, how do you? Let's pretend we didn't look back 2 pages. So what we would do is we would write it as sine x over cosine x. And now the derivative of that, big G prime, which of course is the same as little g, let's do the quotient rule. Okay, you don't have to write this out, but tell me how to write it. So the quotient rule says do what? Derivative of sine is cosine times cosine again minus sine left alone. Derivative of cosine would be negative sine, which would turn that to a plus, right? All over. Now, I could write that as our regular cosine squared, the way you're used to writing it, or I could write it this way. I'm going to write it this way because it's something you're going to see here in about 15 minutes. So, that's what we'd have. Now, what's cosine of cosine? Cosine squared. Cosine squared, because we're multiplying. Plus, what's cosine squared plus sine squared? No. Cosine squared plus sine squared is 1. The entire top becomes 1 over cosine x squared. And 1 over cosine is secant, so 1 over cosine squared is that's the same as 1 over cosine all squared, which is the same as secant x squared. And that's why the derivative of tangent is secant squared. So if you didn't memorize it, you could always just go through this every time. But who would want to do that? I think it's easier to memorize. So the derivative of tangent is secant squared. The derivative of cotangent is negative cosecant squared, and so forth, so on. And we have to memorize those on that page, back on page 163 or whatever page that is. Okay? So that's how you could go about that. Same thing with secant, same thing with cosecant, and so forth. All right? Let's talk about today's lesson. Today's new rule, which is far and away the most important and most commonly used rule in derivatives, because it's called the chain rule. We've already been doing it without you even knowing you were doing the chain rule. And almost every, out of the 10 problems, because didn't somebody ask earlier with Riley maybe, that will it all be quotient rule or all be product rule or was something?
I did.
Or yeah, will it mostly be, or will it be some of those back in chapter 2 or whatever? Of the 10, there might be 2 or 3 quotient rules, a couple of product rules maybe, but almost all of them, 6, 7, will have the chain rule somehow or another in there. And it can have multiple rules in there. We can have a product rule with a chain rule in there as well. Or a double product rule. Or a double chain rule. Or whatever. Now, it's not important that you identify them as such. You don't have to say, oh, this is a double chain rule. You just do it according to what it looks like. So, what does a chain rule say? Well, the chain rule is our way of doing a function inside of another function. F of g of x. Or as your algebra book and this book sometimes calls it, remember the fog notation? Does that look familiar at all? Remember that? That's another way of writing f of g of x, that little open circle. So when you see it in the book, they just mean f of g of x. Okay? But I'm not going to write it like that. But just so when you see it in the problems, you would see it. Okay? So how do we do a derivative of a function with another function inside it? Now, I would suggest to you that we've already been doing that a little bit. When I do sine of 3x, that's a function with another function inside it. 3x is its own function. Okay? And so what have we been doing? We do the derivative of the sine normally, which is cosine. What do we do with the inside? We always leave the inside alone, and we kick out a 3. Now, we've been kicking out the 3 because we said that 3 squeezed the graph. So, therefore, the slopes were steeper by a factor of 3. So, therefore, the derivative had to have a 3 on the outside to make those slopes 3 times as big. So, then the question becomes, what if you had some other function of x on the inside? Like that. What if you had x squared on the inside? What if you had e to the x on the inside? What if you had tangent x on the inside? You know what I mean? What if you had some other function other than just a constant in there with the x? What would that do? It would certainly have to do something to the graph. So it's got to affect the slope somehow. So what would be your first guess at what it would be? Matt?
Like, do the sine x squared, and then
So what do you mean do the sine x squared?
or, I mean, cosine.
So the derivative of sine is cosine. So and we've always been leaving the inside alone, so it kind of seems like we still would. Type in this derivative. Type in derivative of sine x squared. Let's let the calculator do it. Matt's got an idea here. Let's see if he's right. Type in the derivative of sine x squared and see what the calculator says it is. So it's got the cosine like we thought. It's got the x squared still in there like we thought. But what's it got out front? Isn't that the derivative of what was inside? And doesn't that still match what we've been doing? Because 3x is on the inside, the derivative of 3x is 3. So from now on, I won't say we'll kick out a 3. What we'll say is we'll kick out the derivative of the inside. Or we may not say kick out, we'll just say multiply by. That's what we're doing. Okay? So really it's 3 steps. Let's think about what it is here. It's when you have sine of x squared, you do the derivative of the outside. Right? Because what we have is an outside and an inside function here. So we're going to do the derivative of the outside. That's step 1. We're going to leave the inside alone. That's step 2. And then we're going to multiply by the derivative of the inside. Let's write that out in words here. So step 1, take derivative of the outside, or the outer function, maybe we should say the outer function, okay, and take the derivative of the outer function, leave the inner function alone, and then we're going to multiply by the derivative of the inner function. 3 steps. Derivative of the outer function, leave the inner function alone, multiply by the derivative of the inner function. So how would I write this in my rule here? Okay, let's slow down. F prime would be the derivative of the outer function. Then what'd you say? Leave the inner function alone. Multiply by the inner function derivative, d prime of f. That is the chain rule right there. Derivative of the outside, leave the inside alone, multiply by the derivative of the inside. Yeah. And just, that's exactly why it's called the chain rule, because it could go on and on and on, just like links in a chain, or like gears. Different gears, okay? Think of it. And I want to do one like that. Not infinite. But take the derivative of the outside. Take the derivative of the outside, leave the inside alone, but on this 3rd step, when it comes time to take the derivative of the inside, that function on the inside could have something on its inside.
Well, we have one like that.
Absolutely.
I mean, for this test.
Absolutely.
For the one that we're about to take.
Absolutely. So let's do an easy one that doesn't have that, just one more, and then let's do let's do one that does. So let's say we have f of x. It's not that bad. let's say f of x equals natural log wait a minute, I'm going to change that e to the x. I want to make that 3 to the x. So what we have here, until today, we could not have handled it because we did not know how to do a function. We do ln of 2x or something like that, but not ln of some other function side. So, according to the chain rule, the derivative would be what? The derivative of ln x is 1 over x, right? So it's 1 over the inside. So this part right here, isn't that the leaving the inside alone, what I just did there? It is a part that sometimes messes people up on ln. The derivative of ln is 1 over the inside, right? 1 over x. 1 over the stuff that's in there. Leaving the inside alone is leaving that as x squared plus 3 to the x. So by doing that right there, I just did steps 1 and 2. Times, oh, you said quantity, meaning parentheses, right? Again, here's where people would, right, here's where people would mess this up, is they would go times, and now they're thinking, okay, they're thinking derivative inside, so then you totally forget about what you're doing. In other words, you say, okay, now I got a time, so you put a dot, and now you're focused on the derivative of the inside, and so you go times 2x plus, what's the derivative of this? 3 to the x, not plus. And then you write this. I can't tell you how many times I get this, and that'll be wrong. Because am I really timesing by the derivative of the inside here? I'm really only timesing by the 2x, right? The way I've got it written, I'm only multiplying by the 2x. It doesn't matter how big you make this dot. It does not. It's like, seriously, people make that dot really big, so I think that all this goes together or something. I don't know. You've got to have that in parentheses. So when I do these kind of problems, okay, what I typically do, this derivative of the inside stuff, okay, is when I get to that point, and I see kind of a mess of stuff on the inside, I'll say, okay, derivative of the outside is this, leave the inside alone, times, now I'm getting ready to do the derivative of the inside, I'll just put a big set of parentheses like that. Meaning, okay, that's where the derivative of the inside goes. All right, and then I just look at that. I say, okay, that's 2x plus, and then that would be 3 to the x times ln 3. And I only want this ln 3 to times by that, right? I don't want it times the 2x, right? The 3 to the x, ln 3 just attaches to the 3x only. And so then I'm done. Now I could take this and stick it on top, you know, times the 1, so I could move that up there. But this would be fine. Stop right there. So that's a basic chain rule problem. I mean, that would be an easy, I think. Borderline on medium. Why? This might be medium because 3 to the x, you'd have to remember to tack on that ln 3. So maybe you might call that a medium. If it was e to the x there, that would be easy. The e to the x is derivative. All right? All right, let's do one of those that Nick was talking about. That's it. That's your derivative. All right, so let's do this one. Sine of parentheses e raised to the x squared plus x. What is the outside? Well, the outside is sine. The derivative of it is cosine, right? But the outer function is sine. Then the inner function is e to the x squared plus x. But you're right, it has its own outside and inside, right? E is the outside of that one on the inside, and then x squared plus x is its inside. But again, we just start with step 1. Derivative of the outside is cosine. What do we do with the inside? Leave it alone. Step 3 now is multiply by the derivative of the inside. So I put a big set of parentheses. Now in those parentheses, I'm going to do the derivative of this thing in red. So now I'm ready to do that derivative, right? Well, that derivative has an outer function, which is e, and an inner function, which is x squared plus x. So I've got to go through the 3 steps with it. So I'm ready to do the derivative of the red thing, so I do the derivative of the outside. What's the derivative of e to something? It's just e to that same something. We leave the inside alone. So there's steps 1 and 2. I just did the derivative of the outer function of the red, which is the e. It's its own derivative. Leave the inside alone. And step 3 of that is do the derivative of its inside. 2x. Do we need parentheses there? Absolutely. Because listen, what are you doing? You're supposed to take this times the derivative of the blue part. So I've got to take this times the 2x plus 1. Right now, the way I wrote it, it's times what? Just the 2x. This needs to be in parentheses. So anytime you're about ready to do step 3, anytime you're about ready to multiply by the derivative of the inside, I would hit times and put your parentheses. So you have somewhere to put that derivative of the inside. There it all is. Now there's really nothing else I can do with that. This cosine of that has to stay together as one thing. And then it's times this times this. I mean, that's like 3 things multiplied. It's like a times b times c. I could write that b times a times c or c times b times a. I could move those things around, but there's nothing I can really put together to simplify. No. Oh, well, Natalia's saying since this is in a big set of parentheses, don't those two have to stay together? It'd be kind of like if I did 3 times 4 times 5. Do the 4 times 5 have to stay together? No, because I'm going to get the same thing. That's the old associative property. Now, if this in here would have been a big set of parentheses, and then I had this thing, and then a plus this thing, then those would have had to stay together. But since it was this thing times that thing, then they don't. And so, yeah, that's just some of those kind of algebra, arithmetic kind of rules that come back to be pretty important when we're doing these things, especially when we're simplifying. Okay, one last thing. I'm not going to go through the whole problem, but when you have sine squared x, and you want to do that derivative, what's the outside function? No. What's the outside function there? Don't do the derivative yet. Now, sine squared is 2 functions. There's the sine function and there's the square function. Which one's the outside? See, it's confusing. It's confusing. I think some of you said it, but that's what's wrong. That's what I don't like about this notation in calculus. This notation is great in trig, but it's horrible in calculus. What we should, when we see sine squared, we need to think of that as that. Now it's much easier to do the derivative. The outer function is the squared. So what would be the derivative of this one? Bring the 2 down in front, inside alone to the first, times the derivative of the inside, which is cosine. So this would be, and since it's first power, we get 2 sine cosine. All right? Now, if this would have had some other power, if this would have been third, okay, if you end up with a power outside of parentheses, you rarely can do much with it. If I get x plus 1 to the negative 1/2, I can't do anything with that. If I've got a 3 out here, I can't distribute that 3 through there. I can't factor out something out of that. When you get a group of parentheses raised to a power, rarely can we do anything with that. And oftentimes people try to do stuff with it and they can't. Okay? And they try things that aren't legal. All right. So sine squared, so when you see that notation like sine cubed or cosine cubed or something like that, write it like this. Write it like this. It'll make your life a lot easier when it comes to the okay? All right, on the homework, I'm going to take off a couple of problems there. You don't have to do the first 4. So only do 5 through 14. Why, you already been doing them? Seriously? Well, 3 and 4 are so easy.
Yeah. Well, I just started 3. I didn't want to.
And I just thought 1 and 2.
I just wanted extra practice.
And that's very good. All right, so you can skip 1 through 4. So you can go 5 through 14, 15 through 21 on, and then 22, 26. You get to some of those end ones, they're similar to today's 43 through 48, where you have a picture, like a graph or something, you have to do that kind of thing. But on 5 through 14, 15 through 21 on, those are practice on this chain rule idea. And you can see why this is such an important rule, because rarely do you have a function that's just sine x, or e to the x, or ln x. It's almost always got something inside of it. You know, square root of x. We don't have that very much, but we'll have square root of x squared plus 2 or something. Okay, we almost always have something on the inside.
Like you said, not really the sine x and stuff. Still technically that's two functions.
Say that again.
Sine x is still technically two functions.
Why is-
Because what you'd be doing is you're bringing the derivative of x out front, which is 1.
Oh,
So,
I'm with you. So if we have sine x,
so it's
when we do the
technically
derivative of sine x,
1 cosine.
the inner there's still an inner function, which is x,
So,
but its derivative is 1. So, right, so that would be a special case. Yes,
so it's still two functions.
it is. Yes, it is.